Alright, I'm pulling this problem from a different textbook. I didn't really like the problem too much that was in the current book. If I ever do this, I'll tell you what book it comes from. This is Surway and Jewett's 8th edition. I think they're on the 10th or 11th edition now, maybe, so you can totally find this one for free. I was going to use this book, but the rest of the department is using the one that's in our syllabus. Okay, so what we have is a sweet looking airplane right here, and it's landing on an aircraft carrier with an initial, it hits the deck of the aircraft carrier with a speed of 140 miles per hour. We're going to call that approximately 63 meters per second. And it wants to know what's its acceleration if it comes to a stop in 2 seconds. Well, we're looking for acceleration. We know time. We have its final velocity and initial velocity. So if it came to a stop, the final velocity must be 0. We know the time is 2 seconds, and we know its initial velocity. So we can basically go ahead and rearrange this. Let's throw the v0 on this side. Gives us acceleration times time, and then let's divide both sides by time. So what that will give me is the acceleration is equal to the change in velocity divided by the time. And that's a definition we already knew, right? You can always find multiple ways to get back to one definition, but this is literally change in velocity over change in time. They gave us the time, so it's not a delta t really, it's just a t. So plugging in our values, we have it hits the deck at 63 meters per second and it comes to a stop. Sorry, other way around. The final is 0 and it was going 63 meters per second. And we know the time is 2 seconds. We can calculate the acceleration. We're told it should be constant in this case, and we'll start working with non-constant acceleration soon. But I get a negative 63 divided by 2, negative 31.5, and that would be meters per second squared. So negative because it's actually slowing us down. Our acceleration is pointed opposite to the direction of motion. Alright, what else do we got? Part B says if it touches down at what we'll call x is equal to 0 right here. So what actually happens if you didn't know? There's things called arresting cables on the deck, and I think America has 3 arresting cables. I think they used to have 4. And you want to hit the first one with what's called your tail hook, and then that cable just slams you to a halt. It brings you to a stop because otherwise this deck is not possibly long enough for the aircraft to slow down with its own brakes and air brakes. It needs what's called an arresting cable. So how far does it go from this position? How far, we'll call it x, does it make it? What is its position when it's come to a stop? Well, we'll say position when stopped. That's what we're looking for. We're going to use this acceleration we found. And let's go ahead, there's a couple ways to do this. I think it's equation 5 or 4 from the last one. You can use x final is equal to x initial plus 1/2 times v initial plus v final, all times t. I really don't use this formula much. Like literally in dynamics, we don't use that equation at all. It's just the result of eliminating the acceleration variable. Let's use x final is equal to x initial plus the initial velocity times time plus 1/2 constant acceleration times time squared. This one y'all have definitely used before. Let's throw our constant acceleration in there. We know that this is a 2-second interval, so is this. And we have the initial velocity as about 63 meters per second. If we're calling the first arresting cable 0, we can go ahead and cross out the initial position. So we get x final is going to be equal to 63 meters per second times 2 seconds. Those will cancel to give us a meter, and this should come out in meters, right? It's a position. And we're going to add 1/2 times our acceleration, negative 31.5 meters per second squared, times the 2 seconds, and that's squared. Don't forget that one right there. I see that all the time. Well, let me pull out my calculator real quick. 63 times 2, I didn't really need a calculator for, but still. 126, and then I get 2 times 2 times negative 31.5, all divided by 2. Gives me a negative 63. Alright, and adding those together, 126 minus 63 gives us 63. It makes it 63 meters down the deck. Now, the problem has a little what if at the end. It says, suppose the jet lands on the deck of the aircraft carrier with a speed faster than 63 meters per second, but the cable still slows it down with the same magnitude of acceleration. How will that change the distance it takes to stop? Well, we would have a bigger number for our velocity right here. Imagine if this term ended up bigger. Let's even say it was 140 minus 63. 140 minus 63 gives us 77 meters. So, just by having a larger initial velocity when it hits the deck, it's going to have to travel further, even though it's undergoing the same deceleration in this case. Alrighty.